Look at this arrow. It's a vector, and you can also think of it as the coordinates of a point in the plane, like a pixel location measured from the origin. In linear algebra, we don't just multiply numbers, we apply a transformation to space. Now watch this rotation. The direction changes by an angle theta, but the length stays the same. So this rotation moves vectors in a consistent way without stretching them. The faint arrow is the original vector, the bright arrow is the transformed result. Here is the key idea. In the standard basis, a matrix is completely determined by what it does to the basis vectors. The red arrow is E of 1 equals 1 comma 0, and the yellow arrow is E of 2 equals 0 comma 1. If I rotate the whole plane by theta, then E of 1 moves to cos of theta sine of theta, and E of 2 moves to minus sine of theta cos of theta. Now look at the rotation matrix. The first column is exactly where E1 ends up. The second column is exactly where E2 ends up. So a matrix multiplication is not random arithmetic. It is literally where the basis vectors go. Now, why does multiplying by the matrix give the correct rotated vector? In the standard basis, any vector with coordinates x and y can be written as x times e of 1 plus y times e of 2, and a linear transformation preserves this structure. So after rotation, r of theta times the vector with coordinates x and y equals x times r of theta e of 1 plus y times r of theta e of 2. And since the columns of the matrix are r of theta times e of 1 and r of theta times e of 2, so algebra gives a familiar formula. X prime equals x theta minus y sine theta, and y primes equals x sine theta plus y cos of theta. So the takeaway is a matrix represents a linear transformation of space. For this rotation matrix, the determinant is 1, so lengths and angles stay the same. If you remember one thing, remember this: a matrix is defined by what it does to the basis vectors.